Now we looked at the three phenomenon, two types of emission and one type of absorption. Now one thing we need to remember is the electrons which are going from level 1 to level 2 are the ones which are going to be coming back to level 1, right? So something which already belonged to level 2 will not come to level 1 because that electron is fine with being in level 2, that is its equilibrium state. It does not find level 2 unstable. It's only the ones which went up which will come down again. So the number of upward transitions should be equal to the number of downward transitions under normal conditions. So R12, that is the rate of stimulated absorption, should be equal to RSP, rate of spontaneous emission plus rate of stimulated emission. So this is the equation that equates the total absorption to the total emission. So we derived separate expressions for each of these rates. So let us substitute those values. Probability of stimulated absorption times the number of electrons in level 1 times the energy density of incident radiation equals probability of spontaneous emission times the number of electrons in level 2 plus probability of stimulated emission times the number of electrons in level 2 times the energy density of the radiation given for stimulated emission. Yeah, so we have just plugged in the values or the expressions we calculated for each of these. Now we bring both the B terms to one side and you keep the A term on the other side, you get this. You take out rho nu d nu common, you get this expression. You keep rho nu d nu to the left hand side and put everything else on the right hand side, you get this expression. Divide both the numerator and denominator by 2, we get this. Rho nu d nu equals A21, which is the rate of stimulated absorption, divided by B12 N1 by N2 minus B21, where B12 is the rate of A21 is the rate of spontaneous emission, B12 is the rate of stimulated absorption, B21 is the rate of stimulated emission, and N1 and N2 are the number of electrons in the respective levels E1 and E2. So what have we done here? We equated the total absorption with the total emission. We substituted the rate expressions we had, and then it was just simple math, taking common terms together, regrouping LCM and so on. Finally, we have this expression for energy density of incident radiation. Now we will keep that expression with us for a while. This is Boltzmann's distribution for atoms, which if you remember you would have studied in quantum, not in detail, but you would have come across this expression. So the number of electrons or the number of atoms in energy level I is given by this expression. So Ni is equal to G1 N0 e raised to e power minus Ei by kT, where Ni is the number of atoms present in the ith energy level. It is given by Gi N0 e raised to minus Ei upon kT, where Gi represents the degeneracy of the ith level. What is degeneracy? The number of degenerate states that energy level has. So degenerate states as in they have the same energy but different XYZ quantum number. So there is a separate video about that in the chapter on quantum. So if you're not sure about degeneracy, I encourage you to go and check that out. However, degeneracy is not very important to what we're studying in lasers, so you can just remember G as some sort of a constant. N0 is the number of electrons in the base level, the lowest level, e raised to minus Ei, where Ei is the energy of the ith level, upon kT, k Boltzmann constant, T temperature. So this is the expression Boltzmann gave for the number of electrons in the ith, or the number of atoms, in the highest energy level. So this was experimentally determined. Now using that we substitute and we get the values for N1 and N2, and then we do N1 by N2. Why are we doing this? Because in this previous expression for rho nu which we derived, we have this N1 by N2 term. So here we take N1, N2 using Boltzmann's distribution. We calculate N1 by N2, this is the expression we get. So we substitute that over here, you get A21 upon B12, G1 by G2, e raised to E2 minus E1 by kT minus B21. So this is the expression you get for energy density of incident radiation. where G1 and G2 are the degeneracy levels of the energy levels E1 and E2 respectively. What is the degeneracy? Is the number of degenerate states it has. So yeah, this is the expression we just derived. So E2 minus E1 I'm sorry, as we just saw, is equal to h nu, the energy difference between the two levels. So we make that substitution, we get this expression. So this is the expression we have so far. So we'll take a quick recap of how we arrived here and then we'll proceed. So like I mentioned, the total absorption is equal to the total emission. We substituted the values and we got this expression. Now this has something called N1 by N2. So we used Boltzmann's expression, Ni equals Gi N naught e raised to minus Ei upon Kt. We computed N1 and N2. Then we did N1 by N2. We substituted that in the previous equation to get this. This has a term E2 minus E1. So we know E2 minus E1 is equal to h nu. So we made that substitution as well and we arrived at this expression. Now this is the theoretically derived expression for the energy density of the incident radiation which we give. Now Planck had a practically experimentally determined expression for density of radiation, which was this. Now if our whole reasoning and everything we've been learning so far is correct, the theoretically defined expression should be equal to the practically determined one, right? So you equate this to this, and that will only be possible if B12 G1 by G2 is equal to B21 is equal to B. So we'll see why that is. So you assume this part B12 G1 by G2 is equal to B and B21 is also equal to B. Then this part becomes B e raised to h nu by Kt minus B, which you take the B out common, it becomes B e raised to h nu by Kt minus 1. Right, so if you want to bring this e power h nu by Kt thing to this form, that is only possible if this assumption holds. So by equating these two, we understand that B12 G1 by G2 is equal to B21 is equal to some constant B. Then rho nu d nu becomes A21 by B e raised to h nu by Kt minus 1. So when you make this substitution over here, you get this expression. And why do we understand that this assumption, this substitution is a valid one? Because this was a experimentally determined formula. There is no there is no contradiction, or no one has countered this yet. So this is a proven thing. This is true. And what we logically derived is this. So for results to be consistent, these two should be equal, and that is equal only if we make this assumption. So we understand that this is the case. So B12 G1 by G2 is equal to B21, and they both we assume are some constant B. So when you make that substitution, you get this expression. So finally again you take this and compare it with this. A21 upon B is equal to 8 pi h nu cubed upon C cubed. So this is the expression you get, or A21 divided by B rho nu d nu will be e raised to h nu by Kt. So finally, what do we understand from here? This is an important formula to remember, A21 divided by B, which is the rate of A21 being the rate of spontaneous emission, and B is equal to B12 G1 by G2 or B21. So the ratio of A21 to B will be 8 pi h nu cubed upon C cubed, and A21 by B rho nu d nu will be e power h nu by Kt minus 1. These are a couple of important formulae to remember. So a quick recap of these last parts. We know how we arrived here. Now this was an experimentally determined formula. So we equate these two, and we understand that they can be equal only when this holds. So we make this substitution here, we get this formula. Now again you equate these two, you understand that A21 upon B is equal to this, and A21 upon B rho nu d nu will be e power h nu by Kt minus 1. So these are a couple of formulae which you can expect in your numericals and so on.